Bonjour, Madame, Messieurs. It's an honor to be here and continue to elaborate on the relational model that was presented so beautifully by Serge Abiteboul. And I will focus today on two aspects of database queries, logic and complexity. But I want to start with really the one slide that I hope if you remember one thing, you should remember this point, because it's really a philosophical point. During the past 50 years, there's been extensive, continuous, and growing interaction between logic and computer science. In many respects, logic provides computer science with both a unifying foundational framework and a tool for modeling computational systems. In fact, logic has been called the calculus of computer science. The argument is that logic plays a fundamental role in computer science similar to that played by calculus in the physical sciences and traditional engineering disciplines. Indeed, logic plays an important role in areas of computer science as disparate as machine architecture, computer-aided design, programming languages, databases, today's topic, artificial intelligence, algorithms, and computability and complexity, another topic of today. Now, this is a very strong assertion, and it is somewhat surprising, because if you think of logic, it's an ancient kind of philosophical disciplines going back to the classical period in Athens. And then computer science is probably one of the youngest intellectual disciplines, Facebook, smartphones. What do two things have to do with each other? And this was put very nicely by Cosma Arshalizi from the Santa Fe Institute, who wrote, if in 1901, a talented and sympathetic outsider had been called upon, say by grant-giving agency, to survey the sciences and name the discipline, the branch that would be least fruitful in the century ahead, his choice might well have settled upon mathematical logic, an exceedingly recondite field whose practitioner could all fit into a small auditorium. It had no practical applications and not even much mathematics to show for itself. Its crown was an exceedingly obscure definition of cardinal numbers, whatever they are. And now we can jump to 1988, and Martin Davis, a very senior, prominent logician, in an article called The Influence of Mathematical Logic on Computer Science, he writes, when I was a student, even the topologists regarded mathematical logicians as living in outer space. Today, the connection between logic and computers are a matter of engineering practice at every level of computer organization. How did this stunning connection took place? How did it happen? To understand how it happened, we have to go back to incredibly important decades in the history of both logic and computer science, the 1930s. So in response to a foundational crisis in mathematics, Hilbert proposed a new branch of mathematics and logic, proof theory. Until the 1930s, mathematicians used proofs, but they never studied proofs as a mathematical object. And now Hilbert says, we need to study proofs. And the question is, what is a proof? What makes a proof so tight and rigorous that we will call it a proof? And the answer came about that proof has to be so rigorous that a machine should be able to check a proof. Maybe not come up with a proof, but a machine should be able to check a proof. Well, that required that we define machine checkable. What does it mean, machine checkable? And to formalize machine checkability, to formalize the concept of proofs in mathematics, Church, Gödel, Klinig, Post, and Turing had to come up with the very basic ideas that still to this very day are the foundations of computer science. The concept of an algorithm is a fundamental concept. Algorithm, of course, we use all the way with, Euclid talked about algorithms, but they were never studied as an object. And so now we understand the importance of algorithm as a mathematical object, the distinction between hardware and software, the Turing machines, and the instruction for the Turing machines, the revolutionary concept of a universal machine. We talked today about universality, but the idea first came in Turing machine, one Turing machine that can execute every program, and the very concept of programming language. The lambda calculus was really the first programming language. All these concepts come up in one brief activity and creativity in the 1930s. But to understand really where this comes about, we have to go back to the 17th century, where we meet Wilhelm Gottfried Leibniz, who was a real genius and has an absolutely amazing dream for a scholar in the 17th century. And his dream was of a universal mathematical language, which he called lingua characteristica universalis, in which all human knowledge should be expressible. And furthermore, there will be calculational rules. He called it calculus ratiocinator, a reasoning calculus. And of course, Leibniz knew about calculus. He's a co-developer of the differential calculus and also built calculating machines. And so there will be reasoning calculus, and this will be mechanizable to derive all logical relationships. And he wrote, if controversies were to arise, there will be no more need of disputation between two philosophers than between two accountants. So two professors in Collège de France, if they have a philosophical argument, they would suffice to take their pencils in their hands and say to each other, calculemos, let us calculate. So this is an incredibly bold idea that reasoning can be mechanized. And then about 150 years later, we find a huge steps getting close to Leibniz's dream. And Friedrich Ludwig Gottlob Frege writes a small book called Begriffsschrift. Begriff is a concept, language for concepts. And he does ask the following question. What is the language of mathematics? So this is the first time these people are trying to lay what are the foundations of mathematics. An important question is, what is really the language of mathematics? Of course, mathematics, as we practice it, is also a combination of some natural language and some formalism. But if we go beyond that and say, what is really the language of mathematics? And Frege says, essentially, this is first-order logic. The term did not develop for about 50 years, but the basic foundation will lay in Frege. He said every mathematical discourse is about mathematical objects, maybe numbers, relationship between them, or predicates, 2 less than 3, operations on them, 2 plus 3, 2 times 3, logical operation. This was Boole in the middle of the 19th century proposed the study of logical operations, Boolean logic. So you have and, or, implies, not. And a bit after Boole, people proposed quantifiers. Peano and Peirce proposed quantifier for all, and which we denote by inverted A. There exists, which we denote by inverted E. So now you can go back and you can take some of the classical Aristotelian syllogism, which was the very beginning of logic in the 4th century BC. So Aristotle says, for example, all men are mortal. And now to be precise, it means for all x, if x is a man, then x is mortal. And now we can write it now we can write it in a formal notation. This is for all x, if x is a man. So we write, this is a predicate, we write man of x, meaning x is a man. And the arrow implies that x is mortal. So now we can go back to the syllogism, and we can formalize all of them in first-order logic. So first-order logic is now developed in the 20th century as a formalism for describing properties of mathematical structure. So by the beginning of the 20th century, mathematicians have a plethora of different mathematical structures. Graphs, partial orders, groups, rings, fields, and so on and so forth. And generally, every mathematical structure has the same form. There is, first of all, a particular set of elements, and this is called the universe or the domain. So if we're talking about Peano arithmetic, it's a set of natural numbers. If we're talking about real arithmetic, it's the set of real numbers. If we're talking about complex arithmetic, it's a set of complex numbers. Then we have a set of relations. What is a relation? A relation is simply a set of, so Ri is going to be some m-ary relation, which means it's a set of m tuples. So a binary relation is a set of pair, and this is something people start to study around 1870. Then they realize if we're talking about pairs, relationship of pair, then we have also triples, ménage à trois, that's a ternary relationship, and you can imagine all kind of more complicated relationships. So generally, we have an m-ary relationship. It's a relation. And we have n-ary function. It's a function from d to the n to, I'm sorry, to d. This should be here d. It's a typo. So this should be a d. So the argument is that every mathematical structure, that's what it has. It has a universe, a bunch of relations, and a bunch of functions. An example, I'll take two very simple examples. Graphs. Graph has the universe is called the set of nodes, and we have one binary relation, which is the edge relation. So this is a graph. So we have, in this case, one binary predicate. What is a group? A group has the set of elements, the universe of the group, and one binary function. So it's a function from v squared to v. Okay, so this is going to be a group. So in this case, you see there's only one relation, there are no functions. In this case, there's only one function, no relations. In general, you can have relations and functions. So first order logic is, for example, I will now use graph as my running example. First order logic gives us a language to describe properties of graphs. So the variables will always here range over nodes. This is an important point here. The variables always range over nodes, and we'll have two types of predicates. Atomic formula, we can say E of x, y, means there is an edge from x to y, and we can say x is equal to y. And now starting from this formula, using Boolean operations, and using the quantifier, we can form more and more complicated formulas. For example, we can say the following. There exists x, y, and z, and y is different than z, and there is an edge from x to y, and there is an edge from x to z. That means that the node x has two distinct neighbors. So it has neighbors y and z, and these two neighbors are not equal, so they are distinct. Notice here I'm quantifying over y and z, but x is free. This formula is about x. And x could be this node, or that node, or another node. So we call it a free variable. Here we have a formula that does not have any free variable. We say for all x, there exists y and z, such that y is different than z, and there's an edge from x to y and an edge from x to z. So this says that every node has at least two distinct neighbors. So notice this is a property of a graph. The graph either satisfies this property or does not satisfy this property. This is the property of a node in a graph. So there is a difference. One talks about a whole graph. One talks about a particular node in a particular graph. And we will see this is a very important distinction. So in the early days, the distinction between syntax and semantics of first-order logic was not very clear. But this was finally established by Tarski in 1930. And this is very, very important development, distinguishing the language, the syntactical level, and the semantical level. Some people think that this was a great accomplishment. I know that Girard called it the Tarskian travesty. So there is some controversy, perhaps. But for computer science, it was, I think, a very important idea, and it has huge influence in how we think. We think there is a language, a syntactical level, and there's the semantical level in which the program, for example, we have syntax of program and semantics of programs. So Tarski defined it. So Tarski, one of the things he did define was a concept we just saw before of a mathematical structure. That's a definition by Tarski. And then we do have first-order variables. And remember, some of them are free. So we cannot evaluate truth that when we say x has two distinct neighbors, it makes no sense to say whether this is true or false until you bind x to a particular node. Otherwise, when I say, is x equal 0? Well, it depends on x. So we need a binding alpha or an assignment alpha that maps the free variable to particular nodes. So this is the notation we use. We have the graph here. This is pronounced, we call double turnstile symbol. It's pronounced satisfies or models. Here is the binding alpha it binds the free variables to particular nodes, and this is the formula. So it's a G satisfies phi with x1 and xk as free variable under the binding alpha. Okay? So going back to the previous examples, here we'll have to bind x to some particular node. Here there is no free variable, so we really, in this case, we don't need a binding because there are no free variables. Now, Tarski was interested in model theory. So he was really interested in sentences. A sentence is either true or false on a given graph. Either a given graph, is it the case that every node has at least 2 distinct neighbors or not? So we define a set of models of the graph as all the graphs that satisfy the sentence. And this is the beginning of model theory. So model theory studies the relationship between structures and their properties. And in some sense, it's the theory, it's the meta-theory of mathematical modeling, because every mathematical modeling starts by building a mathematical models, and model theory studies how do you describe mathematical models. Now, if you look at the classical textbook in mathematical logic, for example, there is a book by Anderton, had been used by many, many generations of students, and you see that formulas are an uncomfortable, it's an inconvenient object that you need to deal with. You're really interested in sentences, but you define the syntax inductively, and on the way to constructing sentences, you have to have formulas with 3 variables, but they're kind of an annoyance. You're really interested in the sentences because they describe things that are either true or false. And Ted Code made a really brilliant discovery that you can think of formulas as queries. Well, how is that? Take the formula phi, apply to the graph G. The answer would be all the bindings that would satisfy the formula. So in particular, take this formula that says x has 2 distinct neighbors. Now you can think of it as a query. The query would be, give me, for this particular graph, give me all the nodes that have at least 2 distinct neighbors. Okay? So the answer is, give me all the bindings in the form of tuples. So this is a tuple. I'm assuming some ordering of the variables. So the tuple alpha of x1 to alpha of xk, such as G, under the binding alpha satisfy phi of x1 to xk. So this is an incredibly important idea because now we have that logic can serve as a query language. And as Serge mentioned before, if you look what's happening in the 60s, people write very detailed low-level programs to extract data from data, to evaluate queries over databases, even to write a query. If you want to write a query, it's a programming job. And due to the ability to write high-level queries, today we have an industry of over $30 billion a year. Okay? I mean, people argue exactly what you count as relational database industry, but my latest, just before this talk, I learned and done some research, and the current estimate is somewhere around $35 billion. So there are really 2 incredibly fundamental ideas in Code's 1970 paper. One is a simple observation, but it's a profound at the same time. The form of tables, and people have been using tables for a long time, and the table is essentially a relation. So remember, we said a relation is a set of tuples. And a table is a set of rows. And really, the order of the rows in a table does not really matter. You can think of it as a set of rows, and therefore it's a set of tuples. It's a relation. As Serge pointed out, today we are somehow getting away sometimes from this abstraction because we have to portray the table, and maybe you want to sort the table, so the order creeps back. But initially, at an abstract level, you can think of a table as a set of rows, a relation is a set of tuples. Therefore, Code says tables are relations. So in fact, we call it the relational model. Some people call it originally the tabular model because it's based on tables. So this is one very profound idea. And the other idea was that formulas can be served as declarative queries. So we have a declarative programming language. We say what we want, but we don't say how you're going to compute this. So going back to this query, which says list all nodes that have at least 2 distinct neighbors, I'm not telling you how to compute it. I know nothing about the data structure. I'm not telling you how the relations are stored in the database. They happen to be stored in bit trees, but you don't need to know anything about bit trees, and you don't have to write any loop or anything. So this is what I want. Okay, so we have very high-level programming language, and I think to this very day, SQL, which has been evolved from first-order logic, is really the most declarative programming language in wide usage. Logic programming is also, you can argue, declarative, even though this is more debatable. But SQL is probably the highest level programming language that is in incredible usage. And so when people talk about did logic ever have impact on computer science, This is by itself, this is just a relational model by itself, not mentioning any other example. This is profoundly deep impact. Now, of course, you have to evaluate queries. So this is now the topic we're going to go into. We're going to do algorithmic problem in first-order logic. So in some sense, the most fundamental questions in logic is what I call truth evaluation, which also, if you're familiar with the term, it's also called model checking. But I'd like to keep it as truth evaluation. So you're given a formula, you're given the graph or any mathematical structure, but I'll keep using graph for concreteness, and you're giving the binding alpha, and you want to know does G satisfy phi under the binding alpha. This is something that you don't see typically in a classical book in logic, and the reason is because usually they're thinking about mathematical structures such as the natural numbers, the real numbers. Then this does not make sense as an algorithmic problem. But in databases, this is typically a finite, this is a finite graph, it's a finite structure. So this makes perfect sense as an algorithmic problem. I'm giving you the graph, I'm giving you the binding, I'm giving you the formula. Does the formula hold? What you find in classical textbook is usually this question. Given a first-order formula, either some graph and some binding such that the formula holds. This is the satisfiability question. And it's an interesting question because if a formula is not satisfiable, it can never be true. It's a contradictory formula, and so this is some fundamental truth. So typically in philosophy, in mathematical logic, you're interested in the fundamental truth. On the other hand, checking whether something called one graph or another graph, this seems like a contingent truth, and it somehow seems less profound and therefore less investigated. So satisfiability, one of the big results of the 1930s, is that satisfiability in first-order logic is undecidable. Okay? So this is one of the great limits on computation that we discover in the 1930s. On the other hand, truth evaluation, which is, as we said, query evaluation, this is easily decidable because it's a finite graph. So whenever you have for all, you simply have to try out all possible values. And whenever you have there exist, you simply have to enumerate all possible values. And then you just go about enumerating all the truth values of the formulas. So this is easily decidable. So logicians look at it and say, oh, yeah, this is a trivial result. But this decidability is the foundation for the whole database industry. Now, not in the context of databases, but in the context of mathematical logic, in 1976, Fagin proved that graph connectivity is not expressible in first-order logic. So when Code writes his paper, Code has some background in logic, and he thought that first-order logic is the ultimate target of expressiveness. What can be more expressive than first-order logic? But first-order logic became a canonical logic in the context of foundation of mathematics, in particular in set theory. In set theory, if you're trying to do foundations, you want to treat the theory as everything is a first-class citizen. Nothing should be privileged. The only concept is the concept of a set and set membership. And therefore, first-order logic makes sense in that context. But over graphs, for example, turns out that first-order logic cannot say something very simple. You cannot say there is a path from x to y. You can say there is a path of length 5. You can say there is a path of length 517. You cannot say there is a path of unknown length between x and y. So if you have databases that, let's say, describe an airline flying from one city to another, and you want to know, can I fly from here to, from Paris to Timbuktu, there's no query that expresses it. You have to know how many stops are on the way to be able to express it. So this happened in the context of mathematical logic. This is part of Fagin's PhD thesis. And then this result is being rediscovered a few years later by Eho and Ullman. And they propose augmenting first-order logic with fixed points. So I will not introduce fixed point in general, but I'll give you one example here. Here is a simple logic program to describe path in graphs. There is a path from x to y if there is an edge from x to y. So if there is an edge from x to y, clearly this implies there is a path from x to y. Also, if there is a path from x to z and an edge from z to w, again, this is a typo. There is a path from x to w. So these are two simple rules, and they describe paths in graphs. And if you apply them repeatedly, it should be fairly clear that you will prove all assertions about paths in graphs. The first time you'll prove all the paths of length 1, you apply it once more, it will be all the paths of length 2, and eventually, since the graph is finite, eventually you will compute all the paths in graphs. But this requires repeated application of the rules, and you stop when you reach a fixed point. So this can be formalized, and we can get an extension of first-order logic using fixed points. And because we know that first-order logic cannot express paths in graphs, we get, and this has been reproven by Eho and Ullman, that we get a proper extension and expressiveness of first-order logic. And so now people are starting to study different extensions of first-order logic. Sometimes we'll study fragments of first-order logic. So one of the things we see in the 80s is a study of a variety of different query languages. Now people understand there's nothing sacrosanct about first-order logic, and people start studying different query languages. And SQL eventually was extended to include some form of fixed point, some form of recursion. Now I'll start talking about complexity. So the key questions in the 1930s was what can be mechanized? What is computable? One of the great accomplishments, and as you know, as you probably all of you know, this year is the Turing centenary, and Turing was born in 1912, and his biggest contribution is the definition of computability. So this is the 1930s. But in the 1960s, people start to actually build computers. I mean, when Turing defined computability, there are no computers yet. Computers, the first one was really built 1937, I think. So just about the Turing, when Turing proved his result. But by 1960s, people started to actually mechanize this task and that task. And they discovered that some tasks are easier than others to mechanize. So then the questions arose how hard it is to mechanize computation, to mechanize different problems. And people start studying the usage of computational resources. How much resources does it take? And usually we think about time and space. Space is memory. And how much memory does it take? How much time it takes? And we form a hierarchy in terms of the amount of space that is being used or time that's being used. So we have, these are all the problems can be solved using logarithmic space. So if a problem is of size n, you need log n bits of memory to solve the problem. And these are all the problems can be solved in polynomial time, and using polynomial memory, and using exponential time, and so on. And it's not too difficult to prove that log space must be contained in polynomial time, which must be contained in polynomial space, which must be contained in exponential time, and so on and so forth. So this is the first basic complexity hierarchy. Then people discover a very important concept in complexity theory, which is non-determinism. Non-determinism is about checking possible solutions. Somebody proposes a solution. And there is one basic idea here that it's either to be a critique than to actually do things, right? So we have people who are theater critics or restaurant critics, and the restaurant critic is not necessarily a good chef, right? You ask him, OK, can you cook better? No, but I can taste better, right? So this is the idea of critiquing is easy. All of us can come after the lecture and say, oh, yeah, Vardi could have done a better job, OK? But can you do a better job? So this is the distinction between P time and NP time, P and NP. So P is about problem can be solved in polynomial time. We can find a solution in polynomial time, and polynomial time is considered a reasonable amount of time. And NP is a problem can be solved checked in polynomial time. And the beautiful, for example is that if you have a graph and you want to color the graph, color graph means that you assign a color to every node, but you cannot have the same color on neighboring nodes. This comes from coloring maps. You don't want to color two neighboring countries by the same color. So to check if you can do it using two colors is easy, and you can do it in polynomial time. But if you want to do it using three colors, this is NP complete, so we don't know how to do it in polynomial time. So once we add non-determinism, we get a richer hierarchy. So for every class, we also have its non-deterministic analog. So we have that log space is contained in n log space, which is contained in P time, which is contained in NP time, which is contained in P space. This is the one equality we do know. We know that non-determinism does not add to polynomial space, so P space equal NP space, contained in XP time, contained in non-deterministic exponential time, contained in exponential space, and so on and so forth. So this is the hierarchy. And here is the amazing thing about this hierarchy. We do know one thing, So one thing I said, we have one surprise, p space equal np space. We do know that exponential gaps matter. Okay? Exponential gap allow you to show that there is a proof technique. You can show that exponential gap matter. Therefore, log space we know is properly contained in p space. And p time is properly contained in xp time. And p space is properly contained in exponential space. Therefore, this chain of containments, we know that overall, this is an infinite chain. Because we know that log space is probably contained in p space. Somewhere between these, this must break, but we don't know where. And this is one of the most tantalizing questions, not only in computer science, but in mathematics today in general. Where does this break? We know it must break, but we don't know where. So the foundations of the complexity of evaluating relational queries was laid in a really very important paper in 1979 by Chandra and Arel. And in 1981, I'm a graduate student, and this paper just came about, and I start reading the paper. And I read this statement, that evaluating first-order queries is p-space complete. OK. Then I read another one, evaluating fixed-point queries is in polynomial time. Now, it looked very, very strange to me, because we already know pretty much by the time I read it, we know that first-order logic is less than fixed-point logic. So how can this be p-space and this be polynomial time? So at first, and I'm a graduate student, so at first I thought, I read the papers, and all these papers are so impressive and so profound. There's what can I do above it? And there's nothing more to do. Everything has been discovered. Then I see this. I said, well, maybe there is something else to discover here. And so it was clear, and both statements are correct, but it was clear that the theory is somehow not rich enough to explain this confusing situation. And so we need a special complexity theory for relational queries. And I'm going to explain now the classical theory cannot just give you immediate answer about relational queries. So here is the philosophy of how you do complexity theory. So one is you typically look at what we call decision problems. You want a problem that has yes or no, because you don't want to depend on the output size. Suppose I ask you a problem which is to compute something. Maybe the output is very, very long. So it will take a long time just to print the output. So we're interested in problems that are called decision problems. You have to output yes, no, 0 or 1. So the output is 1 bit. So this enables us to get just, OK, how hard it is to compute this 1 bit. OK? And the other one, how do we actually do it? We look at how the usage of runtime or memory grows as a function of the input size. So when I say something is in polynomial time, we say, OK, maybe, for example, it would be in quadratic time. So I say, OK, over graphs with n nodes, you never need more than n square steps. So this we look at how it grows as a function of the input size. So this is really, I describe this as scaling behavior. We look at how it scales up. I'm not saying for this graph of 70 nodes, you can do it in 300 steps. That's not interesting. I want to know how does it scale as the graph grows. So you apply to the database context, and it seems it should be easy. One is, let's focus on Boolean queries, queries that just return yes or no. That shouldn't be too hard. And again, let's look at the input size. What's the input size? Input size should be database size plus the query size, right? We have the input is database and the query. And there is the binding, let's say, also. But I'll ignore the binding for now. And now we run into problem. So, for example, a typical input size would be maybe the database is of size billion, okay, some gigabyte. So database of size billion, and the query is, I don't know, maybe that big, right? In a SQL query, maybe it's that big, so maybe it has 100 characters. So this is the typical size, okay? I mean, notice this is almost negligible here. And now see that, imagine that I can either double the size of the database, or I can double the size of the query. Notice that in this case, the input gets much, much bigger. This, no difference almost. But somehow you have a sense that doubling the size of the query probably can get you later a much harder query to evaluate. So it will have much more impact than doubling the size of the database. Doubling the size of the database, you think, OK, maybe it will double the evaluation time. But this seems much more meaningful. So the intuition here that the database size and the query size, they play very, very different roles when you do query evaluation. And this is not reflected in standard complexity theory, because standard complexity theory just says, let's look at the length of the input. And it doesn't distinguish between these two parts. So the idea that came up in 1982 was to separate data and query. And how do we separate the influence? This is classical idea in computer science, separation of concerns. To look at the influence of the query, we can simply fix the data. We'll take a fixed database. We'll only vary the queries. And to evaluate the influence of data, we'll fix the query, and we will vary only the size of the data. And it turns out that this is not just a theoretical exercise, but there is actually motivation for this. You can think of a situation, for example, in the United States, we do a census, a population census, every 10 years. So the census was done in 2010. Now the data is out, and now sociologists are going to study this data for 10 years. They'll issue different queries, again, the same fixed data for 10 years, until the next census in 2020. Data is fixed, different queries. On the other hand, if you are working in some hedge fund company, you may be looking for some price arbitrage. So you may have one query, but the data keep changing, and you run the same query again and again and again until you find some price discrepancy that you think you can take advantage of. So now you have a fixed query. The data changes every minute. Okay? So sometimes we have a fixed query, sometimes we have fixed data. So we're going to separate them by doing this. So to study query complexity, and this was all done relative to some query language L, and we saw at least two query languages, first-order logic and fixed-point logic. And I'll mention by name other query languages without defining them. So to study the query complexity, we can fix the data. So we're going to study the following complexity of the following set. Look at all the queries in L, such that when you evaluate them on B, the result is non-empty. And the reason I'm doing non-empty, because remember, I don't want to focus on the decision problem, yes or no, without worrying how big is the output. I just want to know, is it non-empty? When you evaluate it, do you get back anything? So here we fix the database. It's a fixed database. We change the query. This is query complexity. Data complexity, you do the other one. You fix the query in the language, and now you vary the data. And you ask, give me all the databases such that when you evaluate Q, this is going to be Q, this is going to be non-empty. So there is two dimensions of the problem. However, there is a subtlety here. So when I do data complexity, which is here, the query is fixed. So the particular syntax of the query almost doesn't matter. It's a fixed query. The syntax of that query does not matter. But when I do query complexity, the query are the inputs. And there is a simple observation that this could be, the syntax become very important. So imagine, look at this thing. This is R cross. Cross is just cross product. It's a very, very simple form of thing. R cross R cross R cross R cross R, blah, blah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? But I can write, suppose you allow me to write something like this. R, maybe star, star, 10. This is much shorter. So which side should I count? Should I look at this size or should I look at this size? So it turns out for query complexity, the syntax does matter. And therefore, we're going to change, instead of calling query complexity, we're going to call it expression complexity, because the complexity in the expression denoting the query. Syntax does matter here. So here is the periodic table that we have for data and expression complexity. And now here I'm going to enumerate 4 languages. First order logic, we saw what it is. Fixed point, I defined by example. And 2 other ones that I won't define. One is essential second order. The other one is partial fixed point. Doesn't matter. This is a chain. These are becoming, as you go up, they're becoming more and more expressive. So indeed, the data complexity is log space, p time, NP, and p space. So you see we're climbing up the complexity hierarchy. So one thing you see from here, expressiveness is not free. You want something more expressive, you're going to pay the price. The complexity becomes higher. Now, the expression complexity is, again, gives us we're going up the hierarchy. P space, X time, next time, X space. But here are the interesting things. Notice each time there's an exponential gap. Log space, P space, P time, X time, NP, next time, P space, X space. So in each case, we see that expression complexity is exponentially higher than data complexity. Now, what's interesting about this is not a theorem, it's an empirical statement. We don't have a theorem that tells us, and the reason we don't have a theorem, because it depends on the syntax, and by playing with the syntax, we can actually we can vary. For example, I can force you to write somehow very verbose queries, and this would lower the complexity, or I can force you to write very succinct queries, and then this complexity will go higher. But this justifies the intuition. This is a beautiful example of the theory. We had an intuition that the query plays a much bigger role than the database in the complexity, and now we see there is an exponential gap. So this is really, I think, a very deep theory that justifies intuition in a very beautiful way. So this is the early 80s. Now, one thing that Serge mentioned is that there's also the relational algebra. So the relational algebra was introduced by Code because not only he talked about using first-order logic to express queries, but he was interested also how does one go about evaluating queries. And of course, we can do the naive way. We can turn every quantifier into just a big loop, but that's going to be very inefficient. So Code introduced the relational algebra, which turned out is equivalent to something that logicians studied before, which was called cylindrical algebra. But because of the strange term cylindrical algebra, he didn't make the connection, so he reinvented the wheel. But essentially, what do we have in relational algebra? We have essentially, first of all, a set operation corresponding to Boolean operations. So we have union, intersection, and set difference. And then you have, for example, a join. So when you have, if you have the logical statement E1 of xy and E2 of yz, you're essentially taking the product modulo that the second argument here has to be equal to the first argument here. So I'll write it join where the 2 equal 1 means the second argument of this equal to the first argument of this. So this is a join. So it is cross product with condition on equalities. And if you have xy such as E of xy, you're taking the relation and you're deleting the second column. And this is projection. Project it on the first column. Okay? So this is projection, and you have also selection, which I'm not introducing here. But essentially, Code's proof, again, it's not a very difficult theorem, that first-order logic is equivalent to the relational algebra. They have the same expressive power. And first-order logic ultimately evolves into SQL. SQL is not exactly first-order logic, but that's why I describe this squiggly arrow. And relational algebra gives the foundation for evaluating first-order queries. SQL queries is based on relational algebra. Okay, so this was a very important development in taking logic and reducing it to actual database management systems. So I think a second important step in laying the theory of the complexity of relational queries had to wait almost to the mid-90s. And at that point, relational databases are already immensely successful and already a big industry by the mid-90s. I mean, you have to remember, Code published his paper in 1970, and he received the Turing Award, I think, in 1980 or 1981, within 10 years. This is one of the quickest Turing Awards between the first paper and the award. Usually it takes much longer than that. So databases are very successful. And the question actually comes up, how come they're so successful? We just saw that query evaluation is hard. Now, you can say data complexity is easy, but this is, if you write different queries, this is very high complexity. I mean, the easiest, which is first-order query, already p-space. Most of us think of p-space as a very hard problem. How come it is so easy to evaluate queries? So the question is, first of all, why is the expression complexity so high? So the answer is that even if you only want to compute one bit of the answer, intermediate results can be very large. For example, this is something that I think when I was in 4th grade, a 5th grader came to me and told me, why don't you compute this product? So I said, OK, 1 times 2 is 2, easy. Times 3, 6. Times 4, 24. OK, now it's 120. Now I need to use a pencil. And I continue until I made the 0 here. And then I said, I should have started from the other direction. So if you have such a join, R1, join R2, join R3, join R4, join R5, it could be that the whole join is empty. But by the time you're here, maybe you have a huge relation that you're computing. So somehow the idea is if we can bound the size of intermediate queries, intermediate results, we're going to get our handle, we're going to be able to bound the complexity. So we want to formalize this intuition, and we're doing it, again, using a beautiful logical theory of variable confined queries. So, and this actually has an analog in the theory of query optimization that Serge referred to. So let's look at these two expressions. So imagine that R1 and R2 are ternary relations. So relations with 3 columns, three places. And I value this expression. It says take R1, join it with R2 by equating the third and the first argument, and then project on the column 1 and 6. So when you do the first join, you'll get a 6-arg intermediate relation. But notice that the middle column of every relation, of both relations, does not really play a role here. I never used the second column. So you could imagine I take the first relation, I project it on 1 and 3. I take this one, project it on 1 and 3. And now I do the join, and I project it on 1 and 4. So now the largest intermediate relation will be 4RE. So this is going to be a smaller relation. This will save me in the evaluation. So it turned out that this is called projection pushing. You try to push projection as low down as possible to get smaller relation. This turned out to correspond to variable reuse, which I'll give you an example in a minute. And bounding the width of intermediate relation correspond to bounding the number of variables. Okay? So now we're going to look at logic, and we're going to study logic with bounding number of variables. Usually when you think of logic, there is a statement somewhere. Variables are going to be x1, x2, x3, ... Variables are free. Use as many as you want. But now we know that we live on a finite planet, and our resources are finite, and we conserve them so we have sustainable development. So we shouldn't think that variables are free. Variables also cost money. So any logic, you can take a logic, and you can suppose I only give you x1 to xk. That's it, nothing more. You cannot use more variables than x1 to xk. Now, this may seem limiting, but you have to be, of course, resourceful. And you have to recycle and reuse resources. So suppose I ask you this statement. Is there a path in a graph of length 2? You say, no problem. I ask, are there x, y, and z, an edge from x to y, and an edge from y to z? This says there is a path of length 2. But I can be more clever. I say, are there x and y, an edge from x to y, and an x such that there's an edge from y to x. I'm reusing x. When I'm reusing x, I forget the previous value for x, and I give it a new value such that there is an edge from y to x. And now I'm able to express the same query using 2 variables by recycling x. I'm reusing variables. So it turned out that if you now limit the number of variables, you're saying, let's look at, for example, a first-order logic, but you are going to bound the number of variables. It's going to be some arbitrary bound, maybe 117, but that's it. You cannot use more. Then let's look what happened. Take the same query language. This was data complexity. This is expression complexity. This is a variable confined the expression complexity. And notice it goes down. P space went to P time, X time went to P time, next time went to NP, X space went to P space. In fact, for these 3 logics, we close the gap. Expression complexity goes down to data complexity if I bound the number of variables. Here, it almost closed it down, but the gap does shrink considerably. So the conclusion from this is that the key to maintaining a reasonable complexity of query evaluation is bounding the number of variables, because then the gap is going to be vanish or at least shrink. And of course, this calls that we immediately have an idea of how we can optimize query. Given a query, try to rewrite it using the smallest number of variables possible. So there is a question. Given any query in first-order logic, can you write it using 117 variables? Unfortunately, about first-order logic, practically nothing is decidable. So this is an undecidable problem. So we cannot do it in general for all of SQL. But we can do it for an important class, which Serge described, which are the conjunctive queries. So conjunctive queries are obtained from first-order logic if you don't have the universal quantifier, and you don't have disjunctions, and you don't have negation. So you can think of it existential, positive, conjunctive queries. And usually we are going to write them in such a rule. Okay, here is an example. I write grandparent xy if, this is read as if, parent xz and parent zy, and here the intention is the z is quantified existentially. If there's some z, such that x is the parent of z and z is the parent of y, then we have grandparent xy. So this is how I would write it in first-order logic, exists z, parent xz, parent zy. And today we write it usually by rule like this. So in general, this is what conjunctive query looks like. And the reason that we choose this particular class, because it turned out the most common SQL queries can be written in this syntax. This is called the select project join queries, SPJ queries, and they cover 90% of the queries that people write in practice. So what do we know about the complexity of conjunctive queries? So Serge talked about query containment, but this is closely related to also query evaluation. We know that evaluate the expression complexity of conjunctive queries, it's NP-complete. And in fact, if we look more precisely, what is the complexity? The answer is going to be size of the database to the power size of the query. It's B to the Q. Now, this is not very nice complexity. And Yanakakis observed in 95, he said, look, this is much worse. Suppose it was this way. Some polynomial in the size of the data, and some small constant to the power exponential in the query, size of the query. So remember, B could be 1 billion. So there is a huge difference, let's say, to 1 billion to the power of 10, which is 1 trillion, and maybe it was 2 to the power of 10, which is 1,000 here, so a much smaller factor here. So it would be much nicer if we can write in this way. And this format, if you can write in such a format, then we say that the query is fixed parameter tractable, because once you fix a query, this is polynomial. Okay, so we would like to get it in this form. So in 1995, he asked the questions, can we take conjunctive queries and put them in this form? This is called FPT, fixed parameter tractable. A couple of years later, together with Christopher Dimitriou, they were able to prove that conjunctive query evaluation is W1 complete. It's not important what is W1 and what is W1 complete. What's important is this is a very strong indication this is not FPT. Okay, so we cannot do much better than this. So the size of the query here is in the exponent. Not very nice. But what about, let's use again the idea of variable confined queries. Suppose remember, we can take any logic and says you only have k variables. So I can take CQ, conjunctive queries, and define CQK, which is only k variables. Now it turns out that if you bound yourself to k variables, then the complexity is going to be the size of the query times b to the k. And for a fixed k now, this is fixed parameter tractable. That's the form we would like to get. So again, what happens if you evaluate this query? If you evaluate this query, this is probably going to be, you're going to use something like n to the cube, because you're going to check all possibility of x, y, and z. But if you look at this one and you're smarter, then it turns out you don't need more than n squared, because you only have 2 variables. So the key is that, the key thing is the number of variables is really the key parameter. So what we learn from this is that it's not the size of the query that matters, but the number of variables that matters. And therefore, we would like to be able to find the smallest k such that the query can be written using k variables. Okay, so again, we'd like to be able to bound the number of variables. And now we get into a branch of graph theory that's called tree decompositions. So the idea of tree decomposition is that we can take graphs like this, and we can make them tree-like by just kind of massaging them and kind of creating bunches, something like this, right? So what I do here, I took this graph and I kind of pushed it and shoved it, and you see that every node now, every bag, we call these bags, every bag has at most 3 nodes, and therefore we call it tree width 2, 1 minus for some technical reasons. So you take the graph, you kind of smoosh it, we get something like this, and now it's a tree. So tree width is a very, very fundamental concept in graph theory, because it tells us how tree-like is a given graph is. So a real tree has tree width 2. A cycle has tree width, 1. A cycle is tree width 2, because I can take the cycle, think of it as a tire of a bike, and I can smoosh it and make it like one line. In fact, it has what we call path width, but it's a thick line. So its tree width is 2. A grid is going to be very difficult to do it. There's no way I can take a grid and make it tree-like. So a grid of size m times m will have a tree width m. There's really nothing I can do about it other than just squish it and get very fat bags. Now, what does this have to do with conjunctive queries? Well, we can define the graph of a query. The nodes are the variables. And whenever you have two variables occurring in one atom, draw an edge between them. And we will say the tree width of the query is simply the tree width of the graph of the query. And it turns out that a query queue can be rewritten using k variable if and only if its tree width is less than k. So the number of variables is really intimately related to the topology. We call it the topology, to the shape of the query. If the query is tree-like and has tree width less than k, we can write it using k variables. And the conclusion is from this, if the query has bounded tree widths, then they're going to be fixed parameter tractable. Okay? So now we get some idea. If you give me the query, I can somehow look at the shape of the query, and I can evaluate it in a way that will be bound by the tree width rather than by the size of the query. So this looks like we have a beautiful theory that we can use for query optimization. We have one little but big difficulty, that it's hard to find the tree width of a graph. Given a graph, you say, what is the tree width? This is NP hard. So I want to use this for optimization, but the very technique itself is by itself going to be a hard technique. So is it doable at all? So let's look at a problem that we know is very hard for databases, which is what happens when you have very large join with many, many, many terms. If you have a very large conjunctive query, and such queries, people don't normally write something like this, but as we know today, we have views, and views defined in terms of views. So by the time you have enough views defined, it's very easy to write a query that really corresponds to a very large joins. And then this corresponds to a very long sequence of joins and projections. And the way optimizer works today, they simply look for the space of possible what they call plans. How can I order it to find the best one? But if the space of possible plans is too large, then the query optimizer, first of all, takes too long to optimize, and it doesn't find a good plan. So with the work I did with the student, Ben McMahon, we said, OK, we'd like to use the idea of tree widths, but we know we cannot evaluate the idea of tree widths directly. So we're going to use some heuristics. And there is a close relationship between conjunctive query evaluation and consensus satisfaction problem that I won't get into. That's a very rich subject by itself. But there is a whole bunch of consensus satisfaction is a hard problem. There's no magical solution about it. But people have been working on it for many years, and we start borrowing some of their heuristic. And we focus on minimizing the size of intermediate tree widths via tree width minimization in a heuristical fashion. So the idea is we're going to minimize the number of variables, but we don't know what is absolute minimum because that's hard to evaluate. So we're going to use a bunch of heuristics. And of course, the idea is that this, to evaluate the heuristic, shouldn't take us too long, instead of trying to find tree width, which is the best possible. So what do we get? We turn out we get actually exponential improvement by using these ideas. So this is what we call the order of the query. This is the size of the join, how many terms the join has. So we start from 5 and we go to 40. So this is when you just give it, we gave it to Postgres SQL, and it grows, this is a log scale, so it grows exponentially. And we pretty much we cannot do much more than about size 10. You know, the timeout, I think, is 1 hour timeout. So after about 1 hour, we stop. Then we try some other heuristics, like, for example, try to reorder the queries, reorder the order of the joins. That doesn't give us much benefit. If we use projection pushing, OK, now we're starting to get some benefit. But if we go the particular scheme that we use, it's not important what it is, bucket elimination MCS. It's throwing a whole bunch of heuristic at the problem. This is still exponential, but you see the slope is now different, and that means we get exponential improvement. So this is still an NP-hard problem, and we don't come up with, of course, we're still going to be exponential, but now we can get to roughly size 40, and before that, we only got at size 10. So I want to conclude here. I gave you the general philosophy of logic in computer science. I want to talk a little bit about what is the role of theory. And this is particularly important in a world today where there is more and more people thinking about, the role of universities would be to create, to to create jobs for students and technology for industry. And we need to take, I think, somewhat a longer-term view of this. And sometimes the role of the theory is simply to clarify the conceptual framework. So to me, you ask, what is the benefit of the distinction between data and expression complexity? It does not lead to better technology. But now we can look at how databases perform with a deeper understanding. And also, I think the theory does suggest to us experimental possibilities. Just suggest. It rarely gives you something concrete. It does suggest. I think Code's relational model is a beautiful example of that. Code was really a theoretician. His papers were conceptual. He did not build any database. After he published his paper in the early 70s, there was a huge war inside IBM. It was called the relational wars, because at this point, IBM itself already has a division selling hierarchical databases based on the tree model. This database is used today by insurance and banks, IMS. And Code is proposing a new model. And the entrenched players, of course, refused to just play nice and say, OK, we'll hand it all to you. There was a huge fight inside IBM. And IBM Research developed System R. And the company did not want to adopt this technology, except that a young, brash guy, Larry Ellison, went to Sigmod, heard some talk by people at IBM, said, great idea. And he came to the market with relational databases before IBM did. And that was the only thing that forced IBM to adopt relational databases. And so it took, after Code's paper, it took almost 10 years before the reality was, before the concept were proved to be feasible. But the theory did suggest experimental possibilities. So that's what I try to give you here, a conceptual framework. And from the theory of tree, which we get some suggestions for heuristic, and we have some empirical result that these can be very powerful heuristics. But again, they have yet to be fully integrated in existing commercial technology. Thank you very much.